Okay. Um, Conning, because a lot of people probably haven't heard of Conning. We've been around for over 100 years. We're located in Hartford, which at least at one point in time was known as the insurance capital of the world. We serve the insurance industry. We are not an insurer, but our clients, by and large, are all insurance companies. We serve them with three different areas of the firm. We manage insurance assets. We are, don't quote me, but I think the fifth largest by assets asset manager of insurance assets. We also provide insurance research. So if people are familiar with Gartner Group, which I bet a lot of this crowd is, we are to the insurance industry what Gartner Group is to IT professionals. Same nature of business. And then finally, we have Risk Solutions, which is the department that I work for. And fundamentally, Risk Solutions licenses risk management software for insurance companies, together with the expertise to help people deploy that software. And sometimes we just provide consulting advice where we use the software to model companies that don't want to undertake doing all that work for themselves. But fundamentally, Risk Solutions is a software business. The lion's share of our revenues come from licensing our software. So what is this software? Well, our core product, which we call Advise, is basically a very large, highly customizable model of an entire insurance company and the exogenous world in which it lives. So embedded within Advise is GEMS, which is our best-in-class economic scenario generator that models the macroeconomies across 16 of the world's largest economies, including a wide range of asset classes, models of credit, mortgage prepayments, and the like, and the ability to model a fairly wide range of derivative instruments. Advise on the investment side models the portfolios of the business, and then on the insurance side we model all the details of insurance, the different products that are being written, the catastrophe risks that are those products are exposed to. We have a management decision function, which basically allows the simulation to simulate the dynamic activities that management would take in response to the situations that the company finds itself in. And we bring it all together with a very large set of accounting standards that we model, various regulatory calculations that are all over the insurance industry, income taxes and other types of taxes. All these things are computed. And the basic point here is that this is a huge model. And what we do is we do a very large scale, multi-period Monte Carlo simulation. So we do this in a multi-period way, and the periodicity varies. Some of our, say, core interest rate and equity return models are effectively continuous time models, so we basically approximate them by simulating at a frequency of about every day. Other parts of the models, the actuaries on the insurance side typically model either quarterly or annually, and so we sync up all these different frequencies. And the state of the insurance company at any one point in time in terms of describing its tax position and all the different carry forwards and carry backs and all that other stuff, and across multiple legal entities and the consolidation of those, this ends up being millions of observable quantities that get calculated and simulated for every time step and every iteration of the Monte Carlo. So we have a tremendous number of variables. Our time periods can be easily, if we're simulating out 50 years and we're doing some of that at daily frequency, tremendous number of time periods. And for property casualty insurers that are exposed to low-frequency catastrophe events that are pretty severe. In order to get an understanding of the tail risk, we often have to simulate 100,000 to 1 million iterations of the Monte Carlo. So basically, in a sense, we're computing this huge cube of numbers with times iteration of the Monte Carlo and these various quantities that are being calculated as the dimensions of this cube. And when you sort of multiply it all out, well, what you get to is maybe 200 trillion numbers that are computed in one simulation, which sort of might seem absurd and unmanageable, but actually not with the technology that's available today. So if we assume, and it's about right, we can on average do 4 million of these calculations per second on a CPU core. That amounts to basically about 14,000 hours of computation if you only were to deploy one core. Fortunately, we can use many cores. If we use 1,280 cores, which is a nice multiple of 32, we can get this done overnight. And yeah, it probably 1,280 cores is probably somewhere around $1 million of CapEx, which is not unmanageable for a large insurer for sure. But better yet, we can rent that 1,280 cores for about $68 an hour on Amazon Web Services, which means we can do one of these massive computations overnight for about $800, which is actually a lot less money than what you paid the analysts to create and parameterize these models, way, way less. Of course, they're going to run it more than once for a variety of reasons, but it's all very manageable. And actually, if you're going to go to the cloud rather than incur the CapEx yourself, you could say, why limit yourself to 1,280 cores? Why not just sort of go all out and say run it on 16,000 cores? It's basically the same price. And that's one of the beauties of doing it in the cloud. So when we started out to build this application, which was basically right at the turn of the century. I love being able to say turn of the century and have it not refer to 1900 anymore. Basically, the challenge that we had was we have this absolutely humongous model. Tremendous amount of effort has to go into building that model, especially if we want to introduce flexibility to morph it in various ways for the needs of various different insurers and the like. So we really couldn't see doing this in a language like C or something like that. It just wouldn't be feasible. It certainly wouldn't be feasible with what the market will bear for selling this software. It just wouldn't make any sense. But by the same token, since we're doing so much computing, unlike some applications where if you're a factor of 10 or 20 inefficient, it really doesn't matter because you're not doing that much computing anyway. Obviously, we're doing tremendous amounts of computing, so performance was very important, the performance on the hardware. So what was our solution at the turn of the century? Well, we decided to use an interpreted array-based language, and clearly the insurance industry and the finance industry has a long history with languages, a number of which were mentioned earlier, APL, A+, K, J, Q, etc. So the problem is when you choose, I mean, the array-based languages gave us the productivity, the interactivity that we needed. The question is, can you get the performance? And the answer is, with array-based languages, you can get performance as long as you can keep doing things as array operations. You don't have to drop down and start doing things scalar-wise. Fortunately, large-scale Monte Carlo is embarrassingly parallel. We got this iteration dimension, which is by definition independent across every iteration. And we chose that iteration dimension for both vectorization and parallelization. So if we have to do 100,000 scenarios, If we do it in blocks of 100, so we have these vectors that are all 100 long, and we're doing all these calculations to do 100 iterations at a time, and then we can do those blocks of 100 across many different computers, we were in good shape. So we had a solution, and yeah, as long as we keep those vectors reasonably large, and they don't have to be that large, once you get to 100, you've got your interpretive overhead down low enough. It's when you amortize over 100 elements of a vector, you're getting pretty good performance, no worse than a factor of 2 slowdown sort of maybe over of what might be theoretically good. So why am I here? And the answer is because this turn of the century solution is becoming problematic, and for some minor and some major ways. So one of those is that array-based languages really require a different mental model on how to program. I was an array programmer for many, many years, so I understand how to translate things into vector algorithms. But array programmers are becoming kind of a scarce commodity, and we're kind of getting old. And they're not teaching array programming languages in academia. So that's sort of an issue. These vector solutions, sometimes it's really simple and really obvious. Sometimes you have to work hard in order to find a good vector solution for various types of algorithms. And sometimes you just can't nail it. There's just the problem that vector algorithms aren't going to give you the performance that you need. Those, I would say, are in the category of issues, but not the thing that drove us. What really drove us is the next two, which is that one of the problems, the drawbacks of this approach that I had by doing these 100 iterations essentially in parallel in vectors was that we now have a memory footprint as we go through this calculation that's 100 times bigger than it needs to be, because we're keeping all this memory for 100 iterations. And so as these models got bigger and bigger, the cache effects and just the complexity just became really problematic to keep trying to fit it all in memory. So we either had to drop below 100 iterations as the model got big, and we dropped our efficiency, or we had to buy tons of memory. But probably the most significant reason is something that I illustrated a little bit further, which is a little bit earlier, which is with the cloud as your way of doing this computation, there's really no extra penalty to scaling up all the way to the point where you have one CPU core per iteration. The problem is, and it doesn't cost you anymore, but we can't deliver if we require to get efficiency, to do 100 at a time. We can't actually achieve that kind of scale. And so as we see this type of simulation, it's just like the poster child for what should be done in the cloud. Rent it when you need it, get it done fast, scale up, but only pay for that computing when you need it. So this is all becoming feasible. And so in order to keep competitive, we knew we had to do something very, very different. One of the things that Viral mentioned earlier, which is an issue for us, we have our quant team, which really does our economic model. And they are typical quants, and they like to use tools like MATLAB. And so we did have this prototype in MATLAB, coded up in a production language kind of thing. And we really think that Julia is going to get them away from MATLAB, and it'll just be natural to do this all in Julia. So what's our solution, which is obvious? It's Julia. And the code is simple. Our job is simpler because we're only coding for one iteration. And so in some cases it doesn't really help. In some cases it helps a lot. It's very high performance. It does give us that high productivity. And it really is, even though there's not a massive body of developers that know how to code in Julia, what we find is that if someone has some combination of C, Python, and MATLAB skills, picking up Julia is really, really, really easy. I also find I always employ summer interns in our shop, And Julia is actually a plus in terms of recruiting. It's exciting, it's new, it's fresh, it's powerful, and so it's actually kind of a recruiting plus to get people on something new and leading edge. It really has the full suite of high-performance array data structures and all the functions to manipulate them. So for people who have a good array algorithm in their head, it just works fine. But if you want to write scalar code, that's high performance as well. And I mentioned MATLAB. So I don't know how much Julia code we're going to see today, but you're going to see a teeny bit right here. So function f, that's how we can define a function. That's pretty simple. A plus bx plus cx squared. The dots, the dot plus, the dot times, that's really saying do it element-wise. So this algorithm will work on vectors as inputs, not just scalars. But it will work with scalars. That dot plus, the dot times has no penalty if you were to feed it scalars. And in fact, the dot plus is actually not even necessary. You would naturally get that without the dot. I do that as a convention to make it clear to me when I'm broadcasting over vectors. The dot times is important because if you just said times, it's trying to do matrix multiplication. But voila, so there's this function f, and what I did was I timed it working on, I think it's 10 million element floating point vectors. So A, B, C, D are 10 million element floating point vectors. And I compared that in our interpreted array-based language. Runs in 374 milliseconds, Julia 227. Comparable. Our array processing language is very, very fast for this kind of thing, but Julia is actually a bit faster. Where it gets interesting, in the second line there, when I say f dot, which is really broadcast, when you execute that expression in Julia, what happens is the function f is going to be called 10 million times, and Julia will deliver to that function 4 scalar floats with each iteration, a, b, c, and x. Julia will create a specialization for that function so that it'll have a version of that will be JIT compiled that will take scalars, which will produce a wholly different set of code than was called on that first line. And it runs faster, in fact, much faster. I don't know if anyone knows why. I do. I know Viral does. I know Jeff does. But the basic reason is in the first case, when you do this vector-wise, we're allocating 80 million byte arrays. We're allocating 5 of them as we go through these vector operations. And our cache performance is kind of nasty because we're running through all these, flushing the caches, right? As opposed to in the second line with the broadcast, what's happening is there's just one allocation of 180 megabyte array for the result, and then everything is scalars at that point, and there's no other memory allocation that's really needed, and that's why we're getting the performance boost. There's also the map function, a functional form, which is essentially does a very similar thing to the broadcast. The next line down, the fourth one, is a comprehension, where we basically zip up these 4 things and basically loop over them element-wise and present it. So again, it's the scalar version of f that's being called on all but the first line. And again, these are very comparable CPU times. And then finally, I've got this function g. So if you just want to sort of write this in a traditional loopy way and allocate R as a result. Similar is basically saying, hey, look at this thing A and get me an uninitialized memory block that's the same as A in terms of length and type. And then it's just running that function in a loop, iterating over all the elements and indexing as we go. And that also runs extremely fast. And so that's the nice thing about Julia is there's many ways to do things. Each of them, in the right application will have its appropriate use, and they're all. Jeff said that they should be the same, right? So, but they're not quite there. So there's a little work to do. But all good enough in my mind.
Each operation takes like 4 nanoseconds.
For each, I'm sorry, you computed it out?
Operation takes 4 nanoseconds.
So how's that compared to what the chip should theoretically do? Not terrible.
We need you to
It's
repeat
squares
the
plus
question.
numbers, and that's
Oh, sorry. So the statement is it's taking 4 nanoseconds per computation.
yeah.
And
So you square 2 numbers and add them up in 4 nanoseconds.
so 4 nanoseconds per result, are you saying, or per individual computation?
But if you go back one slide,
Let's take a look.
yeah, so computing f for just one x, even x, takes 4 nanoseconds.
Right, and it's doing five operations, right?
Yeah.
A square, a times, and 2 pluses. So yeah, so we're basically doing a floating point operation every 8/10 of a nanosecond, which I don't know. Anyone know? These chips are probably capable of.
Pretty good, I would say.
That's pretty good. So what are the issues with moving to Julia? And they are pretty much what you would expect, and nicely, really no more than that. So one is I've got managers, and they're like, "Oh, you're using this new language, and what are the risks associated with that?" And it takes up energy on my part that I would not have to expend if I did something stupid like choose C. And that's management for you. There aren't as many packages as available as compared to something like Python, because it's obviously not anywhere near as popular yet. But for our purposes, it has most of what we need. And it's very easy to incorporate C and Fortran libraries into Julia, so it's really not an issue for us. The language is still in flux, but we're looking forward to release 1.0 in 2017. And because it's in flux, we get to influence it a little bit, and we do from time to time, and it makes us at least feel good, important for something. The lack of experienced Julia developers, as I explained before, really isn't an issue. It's actually a recruiting plus. And I guess I should restrict what I said before about recruiting developers. Recruiting talented developers, truly talented developers, it's a plus. If I'm recruiting a developer whose mindset coming in is what's this going to do on his resume and how can he get another job 12 months from now, well, I don't want him anyway, and probably wouldn't be able to. And then the debugger IDE, these are still works in progress, but they're coming along pretty well. And compared to what we had with our array-based language, we're already in a better situation. So
C++.
I have no regrets.
Can you call C++?
Yes.
Yes.
C and
No regrets whatsoever. Question?
Yeah, considering that Julia is dynamic, and therefore you have no compile time checks, are you all resorting to TDD to mitigate type errors?
Yeah. So the question is, are we worried about type errors because of the dynamic nature and resorting to what?
Test-driven development.
Test-driven development.
Test-driven.
Well, we're separately working towards test-driven development. We're not fully there yet. But no.
Well, apropos the question, isn't that the whole basis of Julia's philosophy? That because it's compiling based upon types, it avoids a lot of that?
Yeah, it does. Yeah, we have very, very few issues with types. So in my example back before, when I declared these functions, I didn't say anything about types.
No, I understand that you're dynamically out. You're
Yep.
sort of saying this, but in a sense, without say a strong static typing, say Hindley-Milner base, how are you, protecting against absurd results because you're jamming one type into something that it shouldn't necessarily go? Something that's notorious in, say, JavaScript, notorious in, or in a sense, hobbles some of Python development.
Oh, yeah, yeah, you can type things. And I didn't in this example, but I sometimes do,
We're
so.
getting a lot of great questions, which we really love, but
Yes.
you're going to definitely have to repeat them, or else we'll be lost forever.
Right, so we're pointing out that typing is optional in Julia.
I mean, do you end up with coercion in the sense of like, let's say I'm shoving something into a float into,
No,
or an
really,
integer
that
into.
isn't, those kinds of problems are not problems, Julia, because from its most inner design out, the way that it treats types is just really smart. Beyond that, I'm going to defer to Jeff.
Yeah,
It's like saying it's magical.
It is.
it is. So,
But actually, we can have a discussion. Jeff can explain all. without
yeah,
explaining,
yeah, I'm not the best person to answer that. I came from an environment where there was no typing whatsoever. And I've never been a C++ programmer. So let's.
Libraries, do you use Python? Is that your favorite ones to use from Python?
I'm using the libraries that have been packaged up for Julia, the Julia packages, and they use a variety of things from Fortran to Python, and I don't have to care. I'm running out of time, and I just wanted to say where we are. Our staff is trained and is productive in Julia. We're still need to train. I think being over a year in, it's time to really take our skills to a next level, and we actually have a class scheduled for next week. And Julia is in our shipping product. That happened a couple of months ago. We're using one of the optimization packages that is available for Julia, and we've written a lot of code ourselves. And we're seeing 5 to 10's performance improvement in many cases where we didn't necessarily expect any. We wanted to be able to match our array-based performance, but we're actually doing much better. So we're happy moving forward. We're looking forward to the fully integrated IDE, a leading edge multi-threading model, and release 1.0 by JuliaCon.
Are your slides available?
Um,
These slides be available?
I can make them available, I think. Yeah.
Yeah, thank you.
Okay.
Okay, thank you.